Welcome back for yet another related rates problem in calculus. This is Airplane 2, the sequel. So that means that if you haven't watched the previous video on Airplane 1, then you might want to go back and look at that first. And there's some terminology in there that is worth going over before doing this one. Not that this is a continuation strictly. Here is the problem. An airplane is flying due west from us. It's 1.4 miles away due west, and it's flying westward due west at an altitude of 1 mile. And we're looking at it through a telescope, and we observe it as having a certain angle above the horizon, which is called the angle of inclination. So I'll describe more clearly in the diagram what the angle of inclination is. We'll call it theta. Assuming that the airplane has a ground speed of 540 miles per hour, then how fast is the angle of inclination changing? So as the plane recedes toward the horizon, your telescope starts going down, 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 so the angle is getting smaller. So you expect a negative value for the derivative of the angle. The question is, what is the rate of change of the angle? So the derivative is going to be a negative, and now I also want you to pay attention to the units. Think about what are some appropriate units. I'll accept an answer in any units, but I want you to be clear what the units are when you express the answer. Let's go ahead and set it up. All right, once again, a little picture just to remind us what's going on. There's a plane flying due west at 540 miles per hour. It's at 1 mile elevation. It's flying away from us. This distance, in the horizontal direction, the distance to the plane is x. There's another distance which is a little bit more, and we've got the angle theta. The line of sight is at an angle theta above the horizontal direction. So we've got, I'll make x depend on theta, and that will give me a trig function that will express x, and if I were to do it the other way, I'd have to do an inverse trig. It's not quite as satisfactory. It's possible to do that way. And the independent variable here will be t for time. So there's our three quantities. The chain rule, dx by dt, that's the ground speed, is dx by d theta times d theta by dt. And I left the most delicate part for the last, which is this derivative. We need to use a little bit of trig. And if you take the tangent of theta, that's opposite over adjacent. So 1 over x, you'd most easily remember as the tangent of theta. And if you take 1 over that, x itself is the cotangent of theta. Now, let's take the derivative, dx by d theta. Just have to remember that that's minus cosecant squared theta. If I substitute that in here, minus cosecant squared theta times d theta by dt is the unknown quantity. On the left side, dx by dt is the ground speed. That's 540. Now I can solve for d theta by dt. So we're going to have to divide by cosecant squared. Well, so just remember cosecant theta is 1 over sine theta. So when you move that to the other side, it becomes sine, and it's squared. So it's minus 540 sine squared theta. And that's everything from this formula solved for d theta by dt. Now we have to evaluate everything at a point in time. Not the time itself that's relevant, but x we know at some point in time when x is 1.4 miles. So when x is 1.4 miles, then we have a right triangle with a 1 here, 1.4 here, and we saw this in the last problem that the hypotenuse is the square root of 2.96. So let me write that in. And we're looking for sine theta. Well, sine theta is opposite of our hypotenuse. So that's 1 over square root 2.96. Fortunately, we're squaring that, so that's convenient. So d theta by dt evaluated at a point in time. Just substitute in when x is 1.4 miles. And that gives us all these values, including the sine of theta. So it's minus 540. And we're taking sine squared. So we take this value squared, and it's 2.96 in the denominator. So that's not too bad. That's actually 182, well, negative minus 182 is the rate of change. And let's remember that theta is in radians. Time is in hours. Now all my distances are in miles. So when I measure this velocity, it's miles per hour. This is in miles, 1.4 miles here. All the distances are in miles. So minus 182 radians per hour. Now just to put that in perspective, I'll just try to change it into something that you can understand. Do a conversion. I'll change this into degrees per second. Degrees of arc, not temperature degrees. Degrees of arc. So the conversion is 180 degrees is the same thing as pi radians. I don't know how you do your conversions, but this is the way that I remember it. So the thing is, I'm not changing the answer. If I multiply by 1, I'm taking this answer and multiplying it by 1. I have a fraction where top and bottom are the same. 180 degrees is the same as pi radians. Why do I multiply that way? Because I want radians to cancel. Units cancel just like numbers do. And radians will cancel with radians here, leaving degrees. By the way, radians is not actually a unit. It's just, radians are just raw numbers. But I wanted to get the degrees in the numerator. And the radians just reminding me, unit, if you think about how theta is measured. So I'll just write it that way. Now, at the same time, I want to multiply by 1 hour divided by 3600 seconds. So I'm multiplying again by 1. Multiply by 1, you don't change the value. But when I multiply by 1, I write that fraction, which is actually a 1, this way, because I put the hours on top because I want it to cancel with this. And seconds will be in the denominator. So when I work this out, it's going to be, it's about minus 0.72 or 73, I can't remember, degrees per second. So that's a little bit less than 1 degree per second. You're looking up at this plane, and your line of sight imagine you were using a telescope or something to look at the plane. You'd have to lower the telescope by about 1 degree, almost a degree, 3/4 of a degree, every second to keep up with the movement of the plane. All right.